Let's check it. We're live. We're live. Looks like we're live. We're live. Looks like we're live. We're live. All right, so can I keep the chat open in OBS? All right, looks like I'm gonna need to. Do a second window. Muted. All right. So, exciting day today. We want to show a pretty cool new feature. Let me adjust this a little bit. As always, let me know in chat if there's anything you want me to change, if you want me to go over anything again, if you want me to change the volume of the background music or anything, just let me know and I'll be happy to do that. Today, we're gonna be doing some pretty interesting stuff, kind of tying into something that we've already looked at a couple of times now. That's why it's part 3 of this series. We'll be looking at optimizing the Parca Flamegraph generation, so the API response that we get back when we render the Flamegraph or Isocograph in the Parca UI. Already in the last 2 episodes, what I think is pretty cool about this is that it's kind of meta, because we can see the Flamegraph generation with the Flamegraphs themselves. So it's kind of meta, but it's pretty cool. And of course, the faster we can make this, the faster people get API responses. This is only one of the parts that use CPU time, but it's definitely one of the major parts. It's roughly 1/3 of all API requests is what we're seeing using this this API call. This code path. So what we're going to be doing today, and let me switch over. What we're going to be doing today is actually we just released a super cool new feature. Let me demonstrate here. We released this feature where you can now view profiling data in line with source code. And we talked about how we made this possible and everything, but today I want to show this this feature live here. And one thing that's super cool and why this feature is so useful, whoops, happened there, is we can kind of go here, say we want to open the code for this, and it'll do that. It'll jump right to the piece of the code that we clicked on, because as we can see here, it was Flamegraph arrow 1358. It jumped right to it. But what's even cooler is something that was really difficult to do before is understand, well, I don't know, looks like we have a bug here. What is this part of the code, right? What is using the CPU time that is the self time of the function? What is the function itself actually doing? And this we can now finally see with this view over here. So we can see this is the cumulative, what all the stacks that are that happen underneath here. So if it's calling a function here, for example, this function call itself isn't using the CPU time, but everything underneath this ended up being sampled twice. So that's super useful, because now we can actually understand what is it in these leaf functions that we can still optimize, right? So in this case, it looks like we're looking at this trim function. It looks like the things that are really using some value, these are all called to other things. But here it looks like iterating over these children is what's causing the CPU time. Now, this is not necessarily a bad thing, and we'll see what we'll optimize. I actually already have an idea or two what we might be looking at today. But I just wanted to kind of demonstrate this feature because I think it's incredibly cool and super useful. We've actually already been using this feature for a couple of weeks internally. We've been trialing it with a couple of customers, and we love it. Yeah, it looks like in this function, the only thing that's actually happening here is this for loop. So it could actually, in theory, also be this array or slice access, or it's just the iteration over this for. So yeah, so trimming is definitely, as we can see, uses about 25%, and what trimming does is it looks at once the whole flame graph is built, it kind of iterates over the whole flame graph one more time to see which frames are even possible to be viewed, because this is a visualization, right? What we're doing is we look at how much screen real estate is there, and if there is any frame that is less than 1 pixel, then any children that, even if we expand it to the full resolution, only had less than 1 pixel, then we actually remove that from the API response. And that ultimately makes the API response much smaller, and the UI has to deal with less data. So all in all, definitely something that we want to do. Now let's have a look. Looks like the main function, let's see where this was, 261. Sorry, what was it? 261. That's just the biggest call. Let's see. Trimming. New transpositions. Yeah, I mean, looks like overall this generate flame graph function seems to be doing quite well. There's nothing super obvious that we can do. It's calling out to some functions to do the actual work. I guess that makes sense. This is a batching function, so I think unless we pass less batches, we can't really optimize this path. Let's see, what is this? Actually appending a row. I mean, this just reads data and writes it again. Aha, growing a slice. I guess append row does that. It has to append. Doesn't look too promising either, but, and this is the one that I was already kind of thinking in the back of my head, this is something that we might want to have a look at. 531. There's something not quite right with the scrolling, but we'll just scroll there. 531. So what we can see here is similar to the other function. We can definitely see that iterating over this, what is it? Aggregate fields. I believe it's a map of fields. Maybe it's a slice. It doesn't really matter which one it is, but it clearly is using CPU time here. And then, wow, even just this if function. I think the reason why this is all so expensive is because this is just probably, and we can see that, but this is called on every single row that is inserted in here, potentially multiple times. Every time we're walking the same stacks multiple times, because, you know, only down here do the stacks potentially differ. We still need to iterate over all of these and add their cumulative values so that ultimately, you know, the flame graph looks the way that it does. This is the function. All I'm trying to say is this function is getting called all the time. It's basically the main thing of actually building the flame graph. So it's natural that even tiny things like iterating over a slice, an if branch are significant. So let's have a quick look at understanding what this thing actually does. So I won't go into everything here about how this is put together, but basically compare rows. Every time we go one step in this flame graph, it's actually funny that I have this flame graph available here to visualize this. That doesn't happen all too often. When we add this, when we go through this, at every level, do we basically check, okay, what are the existing children of this thing? And we add all of the children to the compare rows, and then we iterate through them to find if there's a child by this parent that potentially already has this thing in the stack that we're looking for. And so the compare rows are basically always the children that we want to compare with next. So that's all fine and good, but there's actually something that we could do that should be way faster than doing these comparisons. And it's basically a combination of two things. One, we don't actually iterate over all the comparison fields in every single step. Clearly, we can see that uses some amount of CPU time. In this case, you know, about 2%. Not a lot by itself, but it probably accumulates with all the other things. And as we can see, then 15% are actually spent in doing the actual comparisons. And what I'm leading up to is, what if each child was assigned a key based on the values the fields that we're aggregating by, and then we can just have maps instead of slices that we iterate over and keep doing all these comparisons. What if we had a map that we can just do O of one axis at every level to figure out if this child already exists? So that should be way faster than doing this. So, without further ado then, I'm already in the Parca repository. Let's just make sure that I have everything up to date. I have some benchmarking stuff and configuration still laying around, but we actually let's see. I already checked. I am up to date. So from our previous episodes, okay, we've got Matthias in chat. Hey, makes a ton of sense to replace the looping with a map. Looking forward to the improved performance. Yes, I'm definitely looking forward to that as well. So let's see where we are today. Matthias was saying the music can go ever so slightly more quiet. Let me take care of that then. Let me know if that's better or if I can make it more quiet. All right, so this is our baseline. So I guess we can kind of get started. So the first things first, it looks like we need to replace what we are aggregating by, so that we don't keep iterating over this aggregate field or whatever it's called every single time we do, even if we insert into the map. Clearly it's very expensive to do. So since we need to implement functionality for each kind of comparison anyway, I was thinking we just kind of, while I do actually like this API of just saying I want to filter by function, I want to filter by mapping file, I want to filter by this label, aggregate, of course, is what I meant. And we can just pass that as strings. I like that API from a user's perspective, but I think we should turn that into something a little bit more optimal once we're in this Flamegraph. So new Flamegraph builder. So what I'm imagining is something like aggregation config, so struct, and it currently we kind of only support two things anyway. Actually, the API and the user interface actually only allows two things. Technically, the code allows three things. So the first one is aggregating by function name, and this is actually something that we always have to do. It doesn't make sense to build a Flamegraph that is never aggregated by function name. If we didn't, then all we were doing was listing stacks, and that's not really all that useful. So we're just gonna start with aggregate labels. It's a Boolean, and the second one that we have is aggregate. Maybe it's aggregate by labels, aggregate by mapping file. So how will we do this? I think we already saved it here. Yeah, okay. Okay, so we already have the aggregate. So we'll just move the aggregate labeled into this. So we're do I'll write it out. Aggregate config, aggregation config. Yeah. So this doesn't exist anymore. And then we'll do aggregation config, and we'll loop over the fields. And it's, what is the parameter called? Aggregate fields. We'll change this so that we only pass this in. Actually, we must be already, does it generate? Yeah, okay, so we're already doing this here. Aggregate by labels, and if f equals Flamegraph field mapping file, then aggregation config aggregate by mapping file equals true. All right, I guess we can actually do this directly on the Flamegraph builder. Now we need to write it out. Aggregation config. I'm gonna regret writing this out later, but it's probably for the better for understandability of the code. All right, so first things first. Let's run some tests so that we can see where, well, we broke everything. So okay, we've got aggregation config aggregate by labeled. All right, the first one 179. Next one, config by labeled 100. Why do we have that? That doesn't make any sense. Let's remove that. Again, aggregate by labels. All right. I guess that's probably okay. We probably should remove this. Yeah, I expected more to fail, so. Hello, Nicholas, welcome back to the stream. Let me, my Chrome does not want to today. Let me show you our super cool new feature. What we did earlier was we kind of were looking at a couple of things that we may want to optimize, and I'm sorry, OBS was not cooperating. And by the way, yes, we're back to OBS because we can actually stream in 4K for free, and somehow I like that better. Anyway, coming back to this, what you can do with this really awesome source feature is now we can actually view profiling data in line with our code. And this finally allows us to understand a couple of things. Most importantly, this flat value. What is the function itself actually doing, right? And something that was pretty surprising, at least to me, in this function was it's iterating over a slice that's expensive here. And we ultimately came to this conclusion because this is a function that is called potentially hundreds of thousands of times in a single Flamegraph rendering call. And because it happens so very, very often, a simple if with a pre-calculated Boolean is the same. So I think this is kind of mind-boggling, but we can now actually see this, right? And I think that's kind of exciting. So yeah, that's this super cool new feature. Now we can actually understand how to optimize the functions itself. Thanks, Nicholas. Unfortunately, I can't put, or maybe I haven't figured out how to do it yet, but Nicholas was saying in chat, folks, seriously, this new feature is so hot. Yes, it's really, really cool. We've been actually already using this for a couple of weeks. Quick question, is this only available for Go or any other language as well? Super good question. So at the moment, let me pull up the announcement blog post for this. At the moment, the way it works is that we build a source archive based on the debug info. So it works for any compiled language at the moment. So it works for Go, it works for Rust, it works for C++, it works for C. Anything that ultimately produces a machine executable binary that's not, just in time compiled or interpreted. That said, it's still fundamentally possible to do this with these other languages. It's just, this is what we started with. But super good question. So yeah. And something that it makes this really easy with compiled languages is when we upload the code, we just say the build ID that this belongs to, and that's how we can make sure we're definitely viewing the correct code for this profiling data. We can certainly in the future add things like, link to a GitHub repo and you give us access to be able to view it or something like that, right? Or maybe even a like an IDE plugin, like a NeoVim plugin or VS Code plugin or whatever, that can show it inline. That's all possible because the code for the report is kind of generic. It doesn't have to retrieve the source code as well. But the important part is, are we actually viewing the correct code for this profiling data? And that's something that we can make absolutely sure by matching it based on the build ID. So yeah, what we ultimately came to the conclusion of how we're going to be optimizing this today is the way that this function works is that, and it's cool that we're viewing the icicle graph next to the code that's actually producing the icicle graph. Every time we insert a new stack, we look at, do we already have this function at this depth? Do we already have this function at this depth? And the way that works is that we always iterate over all of the children of a parent and then compare it with the function that we're looking to insert. And that actually doesn't have to be that way. We already know which fields we're going to be aggregating by. And so instead, what we're going to be doing is we're going to be using maps that have O of 1 access, right? Where we don't have to do any comparisons. We just we produce a key for each row, and we just check, do we already have this key in this at this level, right? So we can just do an O of 1 access at every level. So that should be much faster. We'll see. We've already done our baseline benchmark. So now it's the time to actually implement this improvement. So now where did we leave off? We've also got Manuel in chat saying, really nice. Have you considered coloring the cumulative field so that it's easy to, YouTube, it has some emoji over your message so that it's easy to find hotspots when scrolling through the code. That's an awesome suggestion. I don't think we had actually thought of that. but I think I'll definitely be handing that off to the front-end team. I think that's an awesome suggestion to color code the different values of that idea. And actually, something that I haven't mentioned, everything that is done with the source view is persisted into the URL. So if you found something and you want to show it to your coworker, you can just give them the URL, just like everything else in Polar Signals. Everything is always encoded into the URL, so you can paste that onto your Slack or your Discord or wherever you collaborate with your coworkers, and you can be like, hey, this is where this kill happened. That's actually what happened today at Polar Signals, or this is where this optimization is probably going to work best. So yeah, super cool feature. We've actually been using it for a couple of weeks already, very successfully. I've actually been wanting to use it on the stream a couple of times already, so I'm glad we can finally use it here, and that it's finally ready. So the way this is going to work is that we want to remove this aggregate field stuff, and we want to replace it with direct accesses. We've already started a little bit by doing just some piping work where we don't actually pipe the aggregate fields through at all anymore. Although maybe we actually have to. Let's see. No, we're building our, what did we call it? Our aggregation config. And based on the aggregation config, we'll be building the key on each level that we'll do our O(1) access with. All right, so that means this goes away. And compare rows will be a O(1) access. So it'll be something like if row, because the way this is going to look like is that compare rows is right now, let's look at the type. It's of type int. We're going to change that to be a map of, and we're going to be doing an additional optimization here where we're going to be using hashing instead of like hashes of the values instead of like strings or something. We can do this, and we don't actually need to do any hashes. Sorry, we can just combine the integers because everything's dictionary encoded. So we only ever have numbers that we're actually comparing and inserting. So that's another pretty cool thing that we're going to be able to do here. So that's that. And then children is going to be a slice of maps with U and 64. Whoops, that was unintentional. And then we have our roots row that is, yeah, we can just leave like this. All right, cool. So this is going to be row and whether we found it, and fbd compare rows. That. So we'll need something like key. And if we found the key, then we want to do all of this. So we can now remove this. And we can just do that. I'm not even sure. We can maybe come back to this at the very end and see if we even need to set this to be nil. I don't think so, but just being sure, just making sure. All right. So now we kind of can move our way backward, I think. Let's see where merge symbolized rows is called. All right, so we need to build our key. So our key will start with just being 0. No, actually, we'll start with where's equal function name. This is how we access the function name. This is what we already have in our flame graph, and this is the new thing that we want to insert. So we have our translated function name index, and that is what value. Can't do that. Translated function name index. I don't actually know why GitHub Copilot isn't doing anything today. Weird. All right, so we'll start with this, and then we'll do now if our aggregation config says aggregate by labels, and we actually are already hashing our labels somewhere, I believe. We've got our label hasher here. And we've got a label hash. If we are aggregating by labels, and we have labels, then we will have generated a label hash. So we can now do key equals hash combine of our existing key so far, as well as our label hash. And I don't believe we actually have the hash combine function yet here, but we can fix that. And for that, I am going to go to the FrostDB repository, because we have this already somewhere here. This thing, yes, hash combine. Aggregate. Here, hash combine. This is, as we can see, it's something that is pretty widely used and comes out of the C++ Boost library. If you're not familiar, it's probably one of the most used libraries on the planet. If you're writing C++, you probably already know this, but if you're not, then maybe this is new. So hash combine. Basically what it does is it just allows us to combine multiple hashes together. So that's kind of what we're doing here. We have different keys that we want to combine together, right? So aggregation config, aggregate by mapping file. Then we want to do something similar to this. Let's just do the same thing as we did earlier, equal mapping file. We have the translated index. equals combine the comma translated mapping file index. All right, that looks pretty good. Now we actually, this is gonna be a lot of typing through the right things. So 539, let's see what that is. Okay, the compare row that we want to do here. 239. Line row. So the line is K, and the location row is J. Now cannot use translated mapping file index of type in 32. Yeah, okay, makes sense. One, 5, 4. Okay, so this is where a bunch of the piping is gonna need to be quite different. So what copy children does is it basically takes whatever we pass it and it writes it into the compare rows field. And if we happen to need more space, it reallocates. But now what we're actually going to be doing is, and the way that this works is that we always copy the children from some row into this buffer, right? Now we actually don't need to do any of this copying anymore. What we can do is we can just pass over the correct map. So the way that is going to work is it's just fb compare rows. Nicholas was saying in chat, I was thinking about this feature, and if for JavaScript, TypeScript, you could use source maps to achieve this. What do you think? You're absolutely reading our minds. That's exactly how we've been thinking about supporting this for JavaScript and TypeScript as well. Yeah, you're exactly right. It's just that, you know, that's going to require a specific integration, and that's just not the first thing that we were going to do. But you're absolutely right. That's exactly how this would work for those languages. So children sample label row. Nicholas was just saying yay in chat. All right, so okay, so of course we need to not just build our key, but we need to actually pass it as well. Turns out compilers are pretty good. 548. Okay, that's aggregate config dot aggregate by labels, and basically everywhere where we have fb copy children, we can just replace them. Compare rows equals fb dot children of the compare row. Right. This is going to be a, let me remove this function entirely and do fb.compare row. Wow. In this case, we set that to nil for now. All right, that's good. All right, looks like we've covered those cases. Now, what else do we have? 190. Copy children. What was I? It's the same thing. Why? Okay. We'll just that here, because the root row, let's have a quick look at that. What that does is it oops, it should be a pointer to a single integer. Basically, it's a mapping of all the roots that we have to the row in the Flamegraph. We don't actually need this to be a slice anymore. I don't think it ever actually needed to be. It's kind of legacy reasons why it was in the past. So we're a bit lucky here. So I think that's good. No. Cannot use. It's the row, and therefore that goes here, that goes here. How come we don't do this? I feel like that should actually happen here instead. Do we change the type? Yeah. Okay, then we'll change this to be map UN64 to int. And we copy that over. Looks good. And then I guess we can have the label hash down. Roots row. Yeah, we're passing the passing row equals map of UN64 to integer. No, it's the other way around. So it's label hash we actually changed the type of roots row to be label hash to row. Okay, no, that makes sense. Now we can remove this, and everything's nicely encapsulated in this append label row function. Now, wait a minute, if root row is this type and children is this type, then actually we can do something nice now that we couldn't do before. So before we initialized this thing somewhere over here, but now we actually don't need to do this anymore. We can just say that fb dot root row is a map of root 64. I actually like this a lot because we don't have a special case for the root row anymore. So fb children 0 equals, are we reallocating some children? Yeah, least rows, so that's fine, we can do that. And we can actually then do fb root equals root. The reason why we have this is if we're aggregating by labels. Let me demonstrate this. Let me pull up some profiling data. Here we go. Let's go back. If we enable grouping by labels, we actually insert this artificial frame, which is treated as if it was a new root. So in this case, and it looks like we have a tiny bug here that we need to fix. This is the byte number instead of the string, but that's an easy fix. Anyway, it means that we're basically creating new roots. So each of these are a root. So that's why we need to be able to insert multiple root rows. That's kind of the terminology that we chose to go with here. So going back, let's see. All right, that's looking good. I think we can continue where we left off. So now, what is this? We aren't merging this root, so we'll keep track of it as a new one. I think this just means that this. All right, and then if we compare rows equals fb dot children, fb dot roots, root row, label. Use 8. Same deal, fb roots, row, label hash equals row. Fun fact, I actually did start implementing this performance optimization quite a while ago. So some of this does feel familiar, but we kind of threw it out at the time as there were just some more important things, and this was just going to take quite a bit longer. But I know that I was pretty close to fixing most tests. Whoops. So if we totally mess up, maybe we can look at that code. Flamegraph builder has it's roots grow. Nine. Prepare a new record. Yeah, so this is the cool thing now. Actually, we don't need this at all. This is a special case that we needed for the roots row, but now actually we've inserted everything into the roots row, which is already at place 0 in the children. So like this. At this point, we don't care for the individual label roots anymore. We have grouped by them and their metadata before. We can combine all of them into the final children root, making our lives easier later on when trimming and creating the arrow array. This is very recent code. I'm not sure about this. I don't think that this makes sense. This probably was because we had this other code here. So basically, if the length of children is larger than 0, then we reset it and then we add it. I think we can probably get rid of this, but we'll just keep it in the back of our heads in case something goes wrong. 1161, copy children. What is this function? Append row. Okay, so what we're doing here is we're just growing the slice if we need to. So this is just 4, and then we copy the stuff. And now instead of in the slice, we have to in 64. And we'll need to pass our key. And the key is key to row. And this says if I think here now we can check length, but instead we should be checking if this is nil, because if it's nil, then we initialize the map. But if it's not nil, then it's the key equals the row. All right, I think that's correct. 214. Which this is the merge unsymbolized rows, and here actually this is kind of cool that this works out. The way that this works is if a row is not symbolized, then we'll always fall back to merging by the address. And it just so happens that the address is also a uint64. So we can also use that as our key, which is very convenient. So we got kind of lucky there. So I think that's it. No, location row. is J. We had that earlier already. That's correct then. All right. 271. We have not seen, basically what this means is if it got merged, then we continue, but if it did not get merged, that means we haven't seen this stack before while building, and therefore we need to append a new row, and the row has our new key, that is this key. And now 1, 4, 6, 3. Trimmed children. No, that's not children. What was it? 1, 4, 6, 3. Children. Okay, yeah. Map. 4. All right, pretty much the same deal then. Nil. Okay, we're gonna need to build. We need the key again. Although, at this point, maybe at this point, not using a map doesn't make more sense. We just add a new thing that is trim children, that is actually this. Because at this point, we don't need to check for uniqueness or anything anymore. We're only interested in getting a list of each child. So that is better. Okay. Code runs. That's something. Let's start with just this case. That's kind of annoying that it's still running the other tests. But, so... hold on a sec. What's this? 431. Labels only. And that's the... Aha, wait. We're expecting one more, but actually getting this. That's funky. So we're getting one less. Let's print them. So what we're getting is one, two, three, two. And what is the test? We are aggregate function name. And what we're expecting is one, two, three, four, five. All right. Like I said, since I did start this once before, I just want to quickly check if there's anything obvious that we should be doing different. Perf. Oh, already got a branch for that. Maybe that's what we called it last time. Do this work in progress, and then let's label half. So that was similar. That's similar. That's similar. That looks different. Is root has looks something like this. Why is this correct? Why would that be more correct? Let's see what we're doing here. So we're getting the oh shoot. Yes, of course. We need to add this as a child, basically. Okay, so it's this thing. Okay, we've got it. We had a couple of similar places where we did stuff like that. We're here. And we already got a key. That looks a bit better. So what's now different? Oh, just wait a minute. Aggregate function name. is passing. It's passing. So it's just this other thing. We'll have a look at that in a second, but let's run all the other tests. Okay. Mapping file, aggregate nothing. Aggregate nothing, we can probably just remove this test. This just doesn't work anymore. We've removed the ability to aggregate nothing. Hold on a sec. Actually, we should make sure that if aggregate zero, then aggregate don't know. You actually don't need to do this because what was e equal, yeah, we always do this anyway. Okay, so let's just remove that test then. Aggregate nothing. This just doesn't make any sense anymore. Okay. You know what? I think I already see what the issue is. Is there a second aggregate nothing one? Yeah, I think I already see what the issue is with this one. I think because we are using maps now, it's probably happening in random order every time, isn't it? I know, it's actually different. Okay, we'll have to have a look at that one. Sorry, what was the other test? Aggregate mapping file. Hold on a sec. Aggregate, generate Flamegraph arrow unsymbolized aggregate function line. Interesting. Wait, why is that wrong? 117. And it's in 648. Location address. Yes. Before since. It's an order thing. Yeah, okay. Yeah, okay. Okay, that just means we need to introduce some deterministic behavior. That's okay then. And actually at this point, I feel pretty confident that things actually work. We just need to do some small modifications. Oh, dang. I don't know if you remember the times that we started with. Okay, okay. I'm pretty happy with that. What? I did not expect that to be that much faster. Interesting. I think we'll need to do some pretty thorough testing to make sure that this actually works. That's so fast that I didn't expect it to be this fast. Wow, I'm baffled. Faster than I anticipated. I kind of want to look at some profiling data of this. Oops, that opened in my other Chrome tab. Let's see. Take this over here. Okay, looks like it's almost exclusively trimming now, or not exclusively, but you know, we've got 40% of this is generating Flamegraph, so 50% is trimming now. Prepare a new record. Merge symbolized rows. Okay. Now this is interesting. Remember what this looked like before? There was a whole code path in here. This entire code path is completely gone. Equal field just doesn't exist anymore. That is wild. Append row. Okay, yeah, we see the creating the maps is definitely expensive now. Make slice. Where are you making a slice? In append row. Ah, okay, that's whenever we need to grow it. Okay. Interesting. I mean, I won't say no to fast code. But we'll definitely need to do a bit more fixing here. And maybe this one, I don't know yet. Maybe there's still something that's not quite correct yet. But first, let's see what's going on with this one. So clearly there's some non-determinism happening here. But it's only the last two. What is this line? 3, 6, 4, 8. 6, 4, 8. It's the address. Okay, so So this has the children 4 and 5, and these are probably in random order now. But this is the only test we have here, so we don't actually need this to be a table anymore necessarily. So it can be either in this order or it can be this one first. That seems correct, because what we've never seen fail so far is this. This always specifies 4 and 5 as its children, so that's correct. It's just the order. Maybe just to hack this thing. I wouldn't want to merge that. I think though, if we go to from Does this also append new children already? No, I don't think so. Aha, I see. There was a comment in chat, it would be great if you run a profile session for Victoria metrics because they position themselves as a better solution than Mimir and Thanos. We can try to do that. Something that so far has worked really well for us is only profiling things that we actually run ourselves, and we actually just run plain Prometheus servers ourselves. And the reason why I say that is I think it's best if we do these sessions based on real life data, right? And so if there's someone who is maybe evaluating both and is running both, I think then we can have a pretty cool session here. But unless we have two or even one environment that is production stage that we're profiling, that's something that I'm super happy to do. But I think anything else would be pretty synthetic, and the result would be sort of questionable. Because it's not a real representation, right? So I'd definitely love to do all three of those. I'd love to do Thanos, I'd love to do Mimir, I'd love to do Victoria metrics. So if anybody has a production deployment of any of these, I'm more than happy to give y'all access to Polar Signals Cloud. We can profile it and then have a look at this together. So then that way we can actually look at real production data. But great suggestion. Happy to do that if anybody has some environments for us to test it out. Now, where were we? So this is probably the issue. Now, I'm gonna hack this just to see whether this is gonna fix it. Road. And now we're gonna iterate over these. We're gonna append to them. And then we're gonna sort. Oh, I always forget about this. Is it sort bins? Did I get that right? Nice. Okay, and now we iterate over row. Looks like that did fix it indeed. Let's run that a couple of times just to make sure. Oops, got a spell to do this. All right, but let's leave a to do here. We don't want sorting in prod code. It's slow. Remove this and fix the tests instead. All right. Now, let's have a look at our remaining tests. 402. And what did we have here? It's that we are producing one more row than we're expecting. And this test, what is the test case? The test case is aggregate by mapping file. Okay. Let's see. Aggregate mapping file. So it looks like we're passing that in correctly. So we're missing the function for. We have 1, 2, 3, 4, 5, right? And we're aggregating by mapping file. So we've got our functions here. We've got a single mapping. We've got 1, 2, 3, 4, 5. That all looks pretty good. Oh, I think I see it. Okay, so something that we changed in terms of behavior is we will always aggregate by function name. But this test previously tested only aggregating by mapping file, which doesn't really make sense. That's kind of just one step further to not aggregating any stack. So aggregating by function name always makes sense in Flamegraphs. So we don't even want to allow that. So that should mean that we oh sorry, this is the wrong test case. That we break this up. So we should have probably, I'm guessing we'll have location line 4 from power 4 4 4, and what is the cumulative of 4? Location IDs. Yeah, am I understanding it right? It's 3 and 5? Right, let's try test. Not quite. Expected 5.5. Oh, it's the location address. Okay, looks like there might be some non-determinism again here. 409, let's just double check that. 409, the location addresses. Wait, if it's non-determinism, then that should mean that we can just run this a couple of times and see. Doesn't look like it. Is it maybe just that these are flipped around? Is it like this? Or 18? One, two, three. Yeah, that's definitely what we want. Ah, okay. Looks like we're very close now. 4 and 5 are children. All right, the test passes. Now, on to the very last test. 184. 783. All right, so we're comparing children. And we're finding a child that we're expecting nil for. Also, that's pretty weird. That thing that even though we have only 3 rows in total, it's referencing row number 4? What? Everything else is the same. Everything else is the same. I bet it's something about we did something, we renamed something here. We did like trim children or something. Just had ranging over this before. I mean, we can not sure why this would make any difference, but let's just run just that test. Arrow trimming. Wonder if there's something we removed something. We changed something about this thing, roots row. Is that used somewhere? Beats? About children. Is that used anywhere else in the trimming code? Okay, so we're starting with the root row. That's good. That makes sense. Hold on a sec. We removed some code that we said. Let's keep that in mind. What was that code? This point we don't care. Let's put that back and see. So builder diff. Just checking if I inserted it in the right place again. Okay, let's look at it. At this point, we don't care for the individual label roots anymore. We have grouped them by their metadata before. We can combine all of them into the final children root. No, I don't think we need this, but just in case. Oh, look at it again. Just checking though, if in this work in progress stuff that I have on the other branch, if there's anything significantly different there. So let's check out this. So this is roots row, label hash, children nuts row. You know what? I don't think any of this equal stuff is still used. Oh, hold on a sec. Hold on a sec. We totally forgot something here. this whole thing. Shame. I was hoping that would be the fix, but it's not. But now we're going to full field. Yeah, that's totally unused now. We only ever used that for row comparison. So trimmed, building. Oh, hold on a second. New record. Aha! We didn't replace this. Yes! Okay, so now that we've actually fixed everything, let's run our benchmarks again. That's still looking pretty good. Nice. I am very happy with that. 70%, almost 70% faster. Even though we do still have that sorting code in here. And actually, let's just remove that. For benchmarking reasons. Again, I'll probably have to have a conversation with the whole team about that. Oh, it looks like this is even a... No, it's probably just... Yeah, it's maybe a tad faster, but significance doesn't look very large. But yeah, I mean, 68% faster rendering times. I'll take that any day. I think like I said, we'll need to figure out a way to make these tests pass. Let's just make sure that all other tests still pass now. Yeah, it's just this one. But it is almost 6 p.m. here already. I mean, I guess 68% faster rendering I can live with. I'm pretty happy with that. There's probably even more that we can squeeze out of this, but this is definitely a major win for today. So we already had a couple of suggestions in chat today. But if there's anything else, you know, that you think we should be profiling, that we should be trying to optimize, again, super happy to have folks come onto the stream. Maybe we can enable polar signals for them in their infrastructure. We can look at any piece of code that you want in your infrastructure. So yeah, that was Let's Profile September 1st, 2023. We optimized Flamegraph rendering to be almost 70% faster. Pretty happy with that. And with that, please like and subscribe to our channel. That really, really helps us both gauge how popular this is, if we should continue doing it. And of course, it helps us reach more audiences. So yeah, hopefully you enjoyed this episode. Drop by next time again. We had a lively chat. That's always awesome and exciting to see. See you next time. Have a wonderful local time. And if you're viewing, non-live, hopefully you enjoyed the recording. See you all next time.